Let's begin by looking at the function f of x equals 2 to the x. And let's just take a look at what happens. Let's plot a few points here. Okay, so this is called an exponential function, and indeed it's exponential growth. So we'll do x and y equals f of x. So let's do something like -3, -2, -1, 0, 1, 2, 3, and just get an idea of what happens. So -3, right, 2 to the -3 is 1 over 2 to the 3, which is 1/8. So 1/8, all right. 2 to the -2, same idea, 1 over 2 squared, 1/4. 2 to the -1 is just 1 over 2, so that gives us 1/2. 2 to the 0, well, anything to the 0 power is 1. 2 to the 1, anything to the 1 power is itself. So 2, 2 squared is 4, 2 cubed is 8. Okay, so let's plot these out here. The graph goes through 0, 1 right there because of this point. So we have our x and our y, and all exponential graphs that are just in the form b to the x, they're going to go through 0, 1. So this I always think of as kind of an anchor point for exponential graphs. Okay, so let's see. At -3, we were at 1/8, so way down here at -3. -2, we were at 1/4, so up a little higher. -1, we were at 1/2, so right about there. By the time we got to 1, we were up to 2. 2, we went up to 4. By 3, we went up to 8. So we're already off the graph. We're somewhere way up here, almost off the page completely. By 4, we'd go all the way up to 16, so that's way far gone. 5, we're up to 32. 6, we're up to 64, etc. So we could go just to the end of this graph here, and we'd be off several pages up. So this is what exponential functions do. They explode. I like to think of them as exploding functions. So I'm going to carefully trying to graph this here. They come up, they never touch the x-axis, right? They go a little bit off there, right? You want to curve through these points, and then on and on and on they go. And they just keep, they never curl back around or anything. They just keep going up and up and up. There's no asymptote that they hit. They also keep going infinitely to the right, but they go infinitely up much more. Much faster, I guess. So yeah, exponential growth. This is f of x equals 2 to the x. And you can imagine maybe 3 to the x would be even steeper. 4 to the x would be steeper yet. 5 to the x, right? 5 to the x, by the time we got to 1 here on the x-axis, we'd already be up at 5. So that's even steeper. And then you can imagine 10 to the x, 100 to the x, of course. Very, very steep functions. These things explode. They model a lot of situations in nature, mostly things with certain populations. Right? Populations. Populations, interest, which you can think of as population of money. Okay, interest. Chemical reactions, okay, etc. And it turns out a lot of things in nature can be thought of as populations and modeled with exponential functions, at least locally, right? If things really did this, whatever it was doing it, the world would be covered in it in no time. So usually there's some other natural check in nature that brings it back down. Okay, so in general, exponential growth. So we're talking about exponential growth here. When you have f of x equals b to the x, we'll call this the base. And in particular, I'm looking for b greater than 1 for exponential growth. It looks something like this. The graphs are all the same, and essentially you only need to know 2 points. They all go through, assuming there's no shifting or anything, they all go through 0, 1, okay, and then they go through 1, b, whatever b is. Okay, so we have 0, 1, and then up here we have 1b. So depending upon what b is, that tells us how steep our exponential graph is. We go right through there, and off we go, up. But imagine there's no little weird curvies in this like mine has. Right? It's very nice and smooth. Okay, so if you just remember those 2 points, 0, 1 is an anchor point, and then by the time we get to 1, we're already up at b, whatever b is. So the bigger b is, the steeper this jumps up. And that's exponential growth.